Welcome to today's Harvard Data Science Initiative Industry Seminar. I'm Jen Chow. I'm Director of External Engagement here at the HDSI, and it's my pleasure to introduce today's speaker, Kelsey Rogers. Kelsey is an acoustician at Acentech with consulting experience in architectural acoustics, mechanical systems noise and vibration control, and environmental noise. She works on a broad range of projects, including educational, performing arts, commercial, and residential buildings. Kelsey holds an undergraduate degree in mechanical and aerospace engineering from Princeton and a master's in architectural acoustics from RPI. She also teaches architectural acoustics at Tufts University. Fun fact, Kelsey's a pianist, and she brings to all her engineering projects this lifelong passion for performing arts. So before I hand over to Kelsey, I want to remind everyone that we'll be using the Q&A function to field questions for Kelsey during her talk. So please ask early and ask often. And with that, Kelsey, really glad to have you with us, and over to you.
Thank you so much. I'm really excited to be here. So my name is Kelsey Rogers. I'm an acoustical consultant with Acentech. Acentech is a multidisciplinary team of consultants with expertise in a wide variety of areas. That includes building acoustics, which is what I do and what I'm going to talk about in this presentation today. It also includes noise and vibration and technology, and we work on a whole broad range of projects. We're about 75 people. We're based in Cambridge with regional offices nationwide. I'm excited to tell you a little bit more about what we do and how we use data in our practice as acoustical consultants. My background is in music and mechanical engineering. So I grew up as a musician playing a variety of different instruments. Classical piano is my main instrument. As I got to, towards the end of high school and I was starting to think about where I was going to go to school and what I was going to study in college, I knew at that point that I wasn't going to become a professional musician, but I was really dedicated to finding some career path that would allow me to keep that passion of the performing arts really, as an integral part of what I was doing. So I studied mechanical engineering in school, and I got a master's degree in architectural acoustics right after that. And so my path into acoustics has really been this wonderful kind of marriage between music and engineering. I also teach an architectural acoustics class. I'm really passionate about teaching to a great group of mechanical engineering students at Tufts. And I've been doing that for the last several years. So I'm going to start this presentation. The first section here is going to give some background about, what is building acoustics and what is it that an acoustical consultant does, assuming that this may be kind of, new territory to many of you. I'm going to then kind of move into talking about the intersection that I see between data science and acoustics, and in particular, how we use acoustical data over the life of a project to inform the design process. And then I'll finish the project talking about the Harvard Science and Engineering Complex, which I hope is an interesting and a familiar case study that that many of you are aware of and have spent time in that building. I'll talk about the acoustical design process and design features that went into that space. So let's get into building acoustics. An acoustical consultant is typically hired by an architect. The architect functions as really the leader of the building design team, and they hire lots of different engineers and consultants who each have their own areas of expertise that they're giving back, and all of that diverse expertise is really necessary to make the building successful. So an acoustical consultant like me is one of those people, and we're working alongside the mechanical engineers, the electrical and plumbing and structural engineers, sustainability consultants, theatrical consultants, lighting designers, landscape designers. The list is very long. There are all of these different forms of expertise and different disciplines that are a part of the building design, and an acoustical consultant is one of them. Now, if acoustics is sort of unfamiliar territory to you, and you're thinking about, okay, what sorts of spaces would an acoustical consultant work on? The spaces that you're probably likely to think of first are places like concert halls and theaters and other performing spaces. We totally work on those spaces, and we love to do them. They're a particular focus and an area of interest and passion for me, because it's a great combination of performing arts background with design and engineering. But we work on a wide variety of projects beyond those performing spaces too, and that diversity of project type is something that I really appreciate. So we work on lots of educational facilities, and that includes K-12 schools, all of the classrooms and the cafeteria and the auditorium and the gym and kind of all of the spaces that go into a school. in higher ed institutions. So we're going to talk about the science and engineering complex later in the presentation, lecture halls, dorms, campus centers, kind of every building that you could imagine on a college campus. An acoustical consultant probably was part of that design team, or if they weren't part of the design team, they probably should have been. And so there's a lot of work that we do in educational contexts. We also work on a lot of corporate projects, so office fit outs, labs and other sensitive facilities, healthcare spaces, a variety of cultural and civic spaces like libraries and museums and courthouses. The list kind of goes on, but this is just to give you kind of a well-rounded picture of the kinds of projects that we get involved in. And what does that involvement look like on those projects? Well, on any of those project types, you can kind of categorize the input that we are making and the recommendations that we're making over the course of design into three big areas. And those are room acoustics, sound isolation, and the noise and vibration control of the building systems. Building systems meaning, the heating and ventilation systems that are serving the space, the electrical systems, all of that stuff. And each of these are really kind of their own unique category, own kinds of input and things for us to analyze. So room acoustics has everything to do with the shape of the space, its geometry and its size, and the acoustical properties of the materials, like the interior materials that are on all of the interior faces of the room. If you think about the picture that's showing kind of just above room acoustics on the screen, that's the picture of a rehearsal room at Wellesley College. And in that example of a space for music rehearsal or performance, the way that I like to think about room acoustics is that the room is really an extension of the musical instrument. The room, its shape, its geometry, its size, its materials, it fundamentally alters the way that anything is going to sound in that space. And that's a great opportunity and a great challenge to make sure that the room as the instrument is helping is helping the musician to convey and communicate their art to the audience. Sound isolation has almost nothing to do with all of those interior finishes. So everything that impacts the way that something sounds within the room and is in that realm of room acoustics has almost nothing to do with sound isolation, which is how much of that sound that's happening in one room can you hear in the rooms next door. And that's a really common misconception. So sound isolation is really pretty invisible in a completed building. It has everything to do with what the walls are made out of. How heavy are they? Is there any resiliency built into the wall? In other words, are the two sides of the wall decoupled from each other? What is the structural slab of the building? How heavy is it? Again, what's the ceiling made out of and the floor? And are those elements decoupled from each other? Doors, how are they sealed? The windows, all of those components are what go into sound isolation design. And ultimately, working to try to prevent sounds from being intrusive to other spaces nearby. Noise and vibration control, the last category here, is about making sure that all of the systems that the building needs in order to function, the heating, the air conditioning, the plumbing, kind of all of those building systems are quiet enough that they don't disturb what the users are doing inside the space. So if you think about a concert hall, that's kind of one end of this spectrum. In a concert hall, you want the mechanical systems to essentially be inaudible, totally silent, because if you're sitting in, as an audience member listening to a musician play on stage, the last thing that you want to hear is, the hum of mechanical equipment that's serving that room. It's distracting, it decreases the dynamic range of the performance. There's nothing good about that. So we have to work really hard, and it's really important in a music space to make those mechanical systems, essentially inaudible. Inaudibility is not necessary in every kind of space, but noise control design, is really a part of every space. It's just a matter of degree. So in a space like a classroom, the mechanical systems don't have to be silent, but they also can't be so loud that it inhibits communication between students and teachers. And that really does require intentional design thought. If there isn't, it's very unlikely that it's just going to happen to be quiet enough to work really well acoustically. So on a day-to-day basis, our work takes a few different forms. Again, we're working on lots of different project types. Our work kind of falls into these three categories of room acoustics, sound isolation, and noise and vibration control. And on a daily basis, our whole job as a consultant is to communicate, to develop recommendations and then communicate them in a compelling way to that design team. So a lot of what we do is reviewing the drawings that that the architect and other engineers are producing. As an acoustical consultant, we are somewhat rarely actually make drawings of our own. So most of what we're doing is taking, the architectural designs and the mechanical designs. We're reviewing all of that information that they've put into their drawings. We are making our own calculations in the background, and we're using all of that information to inform recommendations that then we're going to figure out how to communicate back to the design team in order for the building to work well acoustically. So there's lots of work in reviewing drawings and doing calculations in the background and then communicating those back. There's also quite a bit of field work. So there are lots of things that we can measure acoustically in existing spaces or in spaces once they've been built near construction completion. We also if we're working on a project throughout the course of design and construction, we visit the site while it's under construction at hopefully several progress points so that we can see as the walls are being built, are they being built in such a way that's consistent with the acoustical design, or is there some kind of education that needs to happen with the contractors to understand how the resilient elements are supposed to be installed or something like that. So lots of kind of drawing and review work, also lots of work in the field and opportunities to make measurements and analyze that data. And then the last of these components is something that really didn't exist a couple of decades ago, but has become, has steadily been growing as a part of our practice in consulting. And that's this topic of 3D listening. 3D listening is an Acentech branded term. The more general term is oralization. So an oralization is a simulation that allows you to hear what a space will sound like before it's built or before it's renovated. And there's an incredible, especially comparative power of being able to simulate simulate a space that is yet unbuilt or, an existing space that's going to be renovated significantly. We can simulate that under a variety of different design conditions, and we can play that back in a calibrated way that is realistic to what it will sound like when it's built. It's not exactly the same, but the accuracy and the realism of that comparative listening experience is very good. And so it really helps to inform design decisions about, how much absorptive material do we need in the space, or what do these walls need to be made out of? It's a real complement to the calculations that we do on an everyday basis on every single project, and that drawing review work and writing reports. 3D listening is a really complementary part of our consulting practice that we can offer. And it's something that applies especially to certain kinds of projects. And it was a big part of our work on the Harvard Science and Engineering Complex. And so I'll come back to that later in the presentation. So at this point, I'm going to switch over to kind of talking about how we use data in the design process for acoustics. And I feel like it's worth mentioning that I don't have a background in data science. I'm talking to many of you that do have backgrounds in data science. That's not what I studied. Acoustical consultants actually do come from a really wide variety of backgrounds, from music backgrounds, architecture, different kinds of engineering. I have not yet met an acoustical consultant who came from a data science background. And yet, I think consulting ultimately really boils down to communicating data in an efficient and in a compelling way to a very diverse group of people in order to try to inform the building design. So that diverse group of people includes the owners and the end users of a space. It includes the contractors that are going to build the building, the architects that are designing the architecture of the building, and all of those other engineers and specialty consultants. That's a really diverse group of people that have, we're all at the end of the day, hopefully working together to make this building be as successful as possible. But our needs are all kind of different. The power of what we're trying to do as an acoustical consultant is, use data in the most effective way possible in order to, communicate clearly and effectively and tell a compelling story through that acoustical information in order to help the design work well. We use data over the whole life cycle of a project, including, at the outset of a project when it's just getting started, throughout design, and after construction has been completed. So I'm going to kind of walk through that design process now and talk about all of the different ways and places that data comes in. So at the project outset, our goal in this first part of design is to set goals for what the space is going to sound like. And we want to do that in a qualitative way as well as a quantitative way. And this is more difficult in some projects than others. In a music space, trying to describe the way that you want a recital hall to sound like is actually a pretty difficult thing to do. Even as an acoustical consultant or as a musician or somebody who thinks about the way that spaces sound a lot, it's really difficult to describe what you want a space to sound like. And that's kind of the first hurdle of the design process, is to develop that shared vocabulary. So music space is on the complicated end of that spectrum. Not all spaces are as complicated as that, though. So, I've put an example here of a classroom that has all hard surfaces. The goal in a classroom is for people to be able to understand each other, and for it to be a comfortable space. So, not so loud when everyone is talking that it becomes uncomfortable and people, feel like they need to leave. So, there's quite a range in how difficult that first step of even just establishing the qualitative design goals can be. Once we manage to do that, ideally what we want to do is be able to map between the qualitative goals that we've set and some quantitative design criteria that we can predict over the course of design, that we can measure in reference spaces while we're getting started, and that we can measure after the building is built and see, did we meet these criteria? Is the building working acoustically the way that we thought that it would, the way that we wanted it to? So let's talk about that simple example of a classroom. Think about a classroom that has all hard surfaces, which means that all of those surfaces are going to reflect sound rather than absorb it. And the experience, in this kind of fictional example, but one that is very common that we see all the time. If you have all hard surfaces in a space, it's, sound is going to build up a lot. It's going to become really loud when lots of people are talking. This is like the classic noisy restaurant problem, not being able to communicate easily across a table, say. And so, having bad speech intelligibility, not being able to understand each other, and just kind of the overall buildup of sound being really loud and uncomfortable. So those qualitative experiences are very well correlated with a quantitative parameter of reverberation. Reverberation is the most kind of, if you know something about acoustics, reverberation is probably near the top of that list. It's a word that is kind of commonly misinterpreted a little bit, but reverberation is like kind of our hallmark parameter. So let's start with that one. Reverberation specifically is the amount of time that it takes for sound to decay to an inaudible level in a space. So if you walk into a room and you clap your hands and you listen to that resulting decay of sound, the amount of time that it takes, from when you clap your hands to when you can't hear the decay anymore, that's the reverberation time. And spaces that have hard surfaces that are all sound reflecting, that sound is going to last, it's going to stick around for a longer period of time. It's going to have more reverberation than a space that has lots of soft sound absorptive surfaces. And speech intelligibility and reverberation are very tightly correlated. So, longer reverberation is going to be worse speech intelligibility and vice versa. And so in this example where we have some, clear qualitative goals, we want to improve speech intelligibility, we want it to be less loud, we have a quantitative parameter that we can use and we can, predict and track over the course of design in order to, inform the design recommendations. So the first thing that we would do in a project like this is an existing classroom, we'd go to the classroom, we would probably, instead of clapping our hands, although we could do that, we'd probably bring a large balloon to blow up, and we'd pop that balloon, and with a microphone we would measure, that resulting sound and use that to calculate the reverberation time. And then there are industry standards for what the reverberation should be in a classroom. And we can compare what we've measured to what those goals are. And, we've kind of gone through that whole project outset process, and we've been able to set qualitative and quantitative criteria. So moving into the design process, how do we use that information? Well, reverberation, the quantity that we've been talking about so far, is also something that you can predict relatively accurately for a simple space based on the room size and its material properties. So in a classroom that's a simple box, if you know something about those materials, you can do a simple spreadsheet calculation that takes into account the volume of the space, the surface areas of all the materials, and then the acoustical properties of each of those surfaces. And it's going to use that information and put it into one equation for reverberation time. And so we can predict what that's supposed to be. And in the example that we're talking about now, where we have an existing space, this is kind of the best case scenario in terms of like clean data, because we've already measured, we know what the reverberation time is because we've measured it, and we can model it pretty well in a spreadsheet model. And so as long as we can get these things to agree with each other, then we're starting out with a pretty well calibrated model of this room, that then we can start modifying some of those materials and use that information to help inform the design process. So in this example, we're trying to get better speech intelligibility, so we need to add some sound absorptive surfaces to the room, and we can use this model that we've built and we've calibrated in a pretty simple way, just in a spreadsheet calculation, to determine the amount of absorption that we need to meet our goal. That sound that we recorded when we clap our hands or if we pop a balloon when we walk into a space, that's called an impulse response. An impulse response really is like kind of the ultimate form of room acoustics data, because it's unique to each combination of a sound source. So in that example, clapping, my hand clapping or the balloon popping, between that, the position of that sound source, and then the position of the microphone or the position of your ears, there's a unique impulse response to that combination of sound source and listening position or receiver that describes all of the possible paths that sound can take from the source to the receiver. The first one of those paths is going to be the shortest one. It's going to be the direct sound. So, straight from the sound radiating right from my hands clapping to the microphone. The next couple, and the kind of resulting decay includes all of those reflected sound paths where sound is bouncing off of other surfaces. It's bouncing off the floor before it gets to the microphone, or it's bouncing off of the wall and then the ceiling and then it's getting to the microphone. And in the early part of this impulse response, those reflections, because sound is only bouncing off of maybe one other surface before it's getting to the receiver, those reflections tend to be large, loud, in other words, and discretely spaced in time. And so they stick out of this thing called the impulse response. And then as you get further in time, you're getting reflections from all around you, and you're getting many, many reflections that are all like very closely spaced in time and space. And that decay, that exponential decay, is the reverberation. So reverberation is kind of the gross parameter that you get from the tail of this decay. But there are all kinds of quantitative parameters that we can calculate from all of the parts of the impulse response. So, what do those early reflections look like? What is their balance with respect to the later reverberation or with respect to the direct sound? Where are they coming from in space? There's a lot of nuance that's built into the impulse response that goes beyond this kind of simple example of reverberation. There are lots of parameters that we can sort of choose from to try to help develop some of the more nuanced qualitative goals for something like a music space to some quantitative design criteria. So we've talked so far about room acoustics, but remember there are three kind of big areas of what we do as an acoustical consultant. So sound isolation is the second one of those that I mentioned. And sound isolation is, so again, this is like, what are the walls made out of? How heavy are they? Are there resilient elements built into them? Same thing for the floors and the ceiling assemblies, the walls, the doors, kind of the whole perimeter construction of a space. And how do those elements prevent sound from transmitting from space to space? And you can write down a mathematical equation for the performance, across the whole frequency spectrum of how sound is going to transmit from, one side of the wall to the other side of the wall. You can, treat that as like a system that has a few masses in it. It has some damping elements, it has some spring elements, and you can make a theoretical model of that, which is all well and good. The only problem is that the results that you get from that kind of prediction are typically for complicated systems that have some springiness and damping to them. When they're actually built in the field, they perform quite a bit differently than what those theoretical equations would predict. So with sound isolation, we are almost exclusively relying on data, on test data, maybe in the field of something that's already been built or something that's been kind of mocked up in a lab and tested in order to predict how sound is going to be isolated, rather than building kind of a theoretical model based on that kind of mass spring damper system assumption. And so that kind of covers sound isolation, and there are a couple of example details on the page of what some of those look like. So the third one of those big categories, noise and vibration control. This is something that we predict. This is a big part of our work, and that we can predict very accurately over the course of design. So the way that this process looks like for us is we are reviewing the mechanical engineering drawings. And on the left side of the screen, you can see a screenshot for the mechanical systems that are planned for a classroom space. So that's showing the mechanical equipment, the duct paths, how large the ducts are, how much air is moving around. All of that is something that the mechanical engineer produced. And then in our job as reviewing those drawings, we can basically take, we can divide that system into all of its individual components. And in a spreadsheet calculation, we can assign noise data to the elements of that path that make noise, like the pieces of equipment themselves, and then attenuation assumptions to the other parts of the path, like the ductwork itself, whether the ductwork is internally lined with absorptive material, how long the ductwork is, if there are silencers in the ductwork which help to reduce noise. So we can kind of reduce or pretty faithfully translate the mechanical engineer's drawings into a spreadsheet calculation to predict how loud is it going to be. Ultimately what we care about is how loud is that mechanical system going to be, in this example, in the classroom. If I'm standing in the classroom, how loud is it going to be? And we want to make sure that it's not so loud that it interferes with speech communication. And so our process during design and this part of our work is to translate the mechanical engineer's drawings, and then we kind of see how loud it would be if we did nothing to the design. And then almost all the time we're figuring out how we can work in recommendations for elements that will help to reduce noise and predict what their performance is going to be, and then work with the mechanical engineer to incorporate those and to work with the mechanical design. So we've talked about Project Outset, setting goals, qualitative and quantitative, tracking those goals over the course of the project through the design process, and what that looks like in our different kind of areas of focus. And then there's a lot that we do after construction as well. So there are quantities that we can measure with respect to room acoustics, sound isolation, and mechanical noise. So we've talked about that with respect to room acoustics, popping a balloon and recording that resulting decay. That's called the impulse response, and there's all kinds of stuff that we can do with that for room acoustics. For sound isolation, we can put a giant loudspeaker in one room, measure how loud it is in that source room, walk over to the next, to the room next door, measure it with a microphone again in there, and measure the receiving levels, and we can say, okay, we know exactly how much noise is being attenuated by that intervening construction. And mechanical, likewise, there's lots of measurements that we can make and then compare back to those design goals that we set. So I've talked a bit, I talked about this kind of idealized classroom example of the existing classroom with all hard surfaces. It's too loud, people can't understand each other. That was an example where we have quantitative project criteria. They are well correlated with qualitative goals, and we were able to articulate those qualitative goals pretty easily. We were able to predict the quantitative goal during design well, so we were able to build a reliable spreadsheet model of reverberation and add different design components to that and see what impact it would have. And then we could go back to that classroom after they've installed the sound absorbing treatments and repeat that measurement. So pop our balloon again, measure reverberation, see if it has been reduced as much as we thought it was going to be. That's a pretty nice closed loop system, and that applies to some of our projects, but not all of them. So many real projects that we work on are much more complicated than that, and that complication can come from a variety of different sources. So one of those places is it can be very difficult to agree on what the qualitative goals are, the kind of first step, especially in a music space. and again, especially in a music space, it's very difficult to correlate quantitative metrics with qualitative goals. This is a field that's growing all the time, and there's a lot of research in this area about trying to identify new parameters that we can calculate and have them, more closely tied to the perceptual experience. But there's still a lot kind of missing there. Another reason that this can be challenging is if the space has a really large volume, like geometric volume, and if it's a very complicated geometry, especially if it's one that's not similar to anything else that already exists. This is like going to be a very kind of novel building construction or shape of a space. Just to be kind of transparent, a lot of the time the input that we get after construction, we often don't hear about projects unless there is a problem, unless we kind of have like a specific part of our scope to return to the site and make measurements, which we try to do as much as possible. But on a large number of the projects that we do, we don't get the opportunity to do the follow-up measurements. That would be a great opportunity to help kind of close that loop and keep improving the data that we have, but it's not one that we always get. So I'm going to spend the last portion of this presentation talking about the Harvard Science and Engineering Complex. So I hope that this is a project that people are familiar with. I also hope that if you've been in this space that the acoustics have either been noticeably good or at least not detracted from your experience. And I'm going to talk about how we kind of leveraged acoustical data throughout the design process of this one. So this is a massive project. This is over 500,000 square feet of space, designed by German-based architect Banish. 3 kind of major wings that are all connected by this multi-story interstitial atria. Many kind of atrium spaces that are all linked together. And there were all kinds of really interesting acoustical challenges in this project, but I'm going to focus on the atrium space in particular. So this is a couple of images of that atrium space, or one of them. There are a few of them that are all kind of interconnected. Now, this is an example of, the qualitative goals are not so difficult to describe, and actually they're not really that different from the classroom example that we just talked about. So presentations happen in this atrium, and we want speech intelligibility to be good. We want people to understand what presenters are saying, easily. And we want user comfort. So when there are lots of people moving around and having their own conversations, we don't want that to become so loud that it's uncomfortable for people to be in the space. Those are exactly the same 2 goals that we had for the classroom. The difference here is that this is a much, much more complicated geometry than we had before. Another goal that I want to mention is because this big atrium is what's kind of connecting the whole building that's kind of the central portion of the building that's connecting a lot of things together. And so there are a lot of spaces that overlook that atrium, that open directly onto it. And thinking about sound isolation, how much of that atrium activity noise is going to be transmitted into each of those spaces and how much is acceptable, that was a big part of our work as well. So the qualitative goals, not so hard to describe for this project, but the first roadblock that we run into is mapping those into quantitative criteria. So reverberation time, this is, in the classroom example, we had an industry standard for, what the reverberation time should be for the classroom. We're not going to have that for this kind of, yet to be built, very complicated atrium space that's different from every other atrium space in size and shape. And there are ways around that. So there are other parameters that we can use that kind of remove that geometric volume from the calculation. We can use something called the average absorption coefficient. And we do have some kind of comparison points that are helpful from that perspective. But the problem really is that because of the complexity of the geometry of this atrium, it would really not be not accurate, not reliable to try to predict reverberation in the same way that we did for the classroom. The classroom is a 6-sided box, very simple closed volume. But that we can do that all day. That's easy for us to predict with a spreadsheet model and map that. Make sure that that's calibrated well with measurements. Three different kind of linked atrium spaces where none of the floors line up. There are lots of kind of open hallways for sound to go down. That's not a good case for trying to map that into a simple spreadsheet model and expect to get reasonable results that would match, the reality after construction. So this is where 3D listening came in on this project. And 3D listening ultimately is really leveraging the data of an impulse response. So remember, an impulse response, we talked about it before in the context of measuring it in a room, so popping a balloon or clapping your hands and recording that resulting decay, which is all of the possible paths for sound to take between a source and a receiver. This is something that we can simulate. We can build a geometric model of a space, based on the architect's model, with some simplifications that we need to make in order to run our acoustical model. And what we're using are mostly ray tracing algorithms. So we can define, okay, a presenter is going to be standing here. Let's simulate what it sounds like with groups of people standing in all of these different places. So our sound sources are going to be populated with, in this example, hundreds of thousands of rays that represent sound that radiates off of each of those sound sources. And we can also populate that model with listening positions or receiver positions. And over the course of that simulation, those receiver positions are basically just kind of hanging out in the model and waiting to collect all of those paths for sound. So if they're waiting for all of those rays to kind of intersect with that receiver point, and they're collecting that information, and that is essentially the simulation of an impulse response. It is not exactly going to match a measured impulse response, but it can get relatively close. And what I said earlier in the presentation is that even if the kind of absolute accuracy is not 100% there, what is very accurate and reliable is the comparative listening experience. So we can run a model with, say, all of the ceilings in this atrium are going to be sound reflective. And then we can run the same model, but we can change the acoustical properties of all of those ceilings to be an absorptive material. Or we can do that to some of the ceilings and some of the walls, but not all of them. And when we listen to the comparison between each of those models, that experience is reliable and accurate, and ultimately a really powerful form of consulting and communicating the acoustical data that we have. So once we've simulated an impulse response, the impulse response is just going to sound like somebody clapping their hands in the space, and that's not what you want to listen to. We can combine that in a special way with audio that has been recorded, specifically for this purpose. So you can make a recording of any kind of sound source in a space called an anechoic chamber, or a space that has all sound absorptive surfaces, so that it has no room acoustics of its own. When you make a recording of a sound source in that room, the only thing that you are recording is the sound from that instrument or that person talking or that sound source itself. And when you combine that anechoic audio with an impulse response, and then you play that back in a calibrated way, we tend to do it over a loudspeaker array. You can do it over headphones with some caveats. Once you kind of go through all of those steps, the result that you get is, this is essentially what that person talking is going to sound like in this space. And again, when we build these things, we simulate the model under several different design conditions so that you can have that comparative listening experience. And the questions that we were trying to answer over the course of this project, and specifically for the 3D listening experience, were how much sound absorptive material do we need, and what do we need to do to prevent that atrium sound from disrupting adjacent spaces? And so on the topic of sound absorption, at the point that we did this 3D listening experience, it was kind of midway through design. So there was already quite a bit of sound absorption built in. And the question is what's in the design enough right now? We don't have, without doing this simulation, we don't have a really accurate, believable method of estimating the reverberation time, or really like a good goal to work off of. And so we're going to use this listening experience to say, is what we have in the design enough? Is it worthwhile if we compare that to what it would sound like with no absorptive material? Does that difference, is that worth all the cost that's associated with all of that absorption? And if we find that we need more, how much more would we need to do to make a difference? Where should it go? All of those questions are kind of what gets wrapped up into this oralization exercise. And then on the topic of sound isolation, this was really largely about doors. So are the door locations to all of those classrooms and meeting rooms and offices, are those locations appropriate, or should they be moved around the corner? Which doors need to be sealed? Which rooms should have a vestibule entrance? So 2 sets of doors to go into in order to isolate sound from the atrium and prevent disruption to those spaces. So this is a screenshot of that interface that we used, and I'd be happy to host anybody at Acentech if you'd like to listen to what this sounds like. This is the kind of thing that works really best over our loudspeaker array listening system. So unfortunately, I'm not going to play this for you right now, but what we were able to kind of show through this demonstration, we could listen to different levels of absorption. We could listen from different positions. So from the first floor, the second floor, different areas relative to a presenter, different activity levels. So, what does it sound like just sort of mid-morning when there are people milling around and having conversations versus maybe at a class changeover time when there are lots of people moving around, or when there's an event happening, a cocktail party. We could simulate those different levels of activity. And one of the other elements that I just want to call your attention to that was in this particular demonstration was reference to an existing space, to the existing science center. We went to that kind of familiar atrium space to people on the design team and people from Harvard, and we made recordings and acoustical measurements of activity at different times of day. And then we put that into this presentation so that we could all listen to that as a reference point. And then compare, not only compare kind of the simulation of the new yet to be built space under different design conditions, but also, use that kind of calibrate your listening experience to what you're used to in this, in this existing space, and use that as a reference point as well. So ultimately, the outcomes of the 3D listening were confirmation of the design concept for absorption, which in this building is really all about the ceilings. Because it's such a complicated geometry, there is a ton of exposed ceiling area. None of the levels don't exactly line up with each other, which means that there are all sorts of kind of, partial levels and levels that stick out into that atrium space. And what that means for us acoustically is that we have lots of potential surface area for absorptive treatment. So everywhere in this building that you see this kind of slotted wood system, there's absorptive material behind, just above that. And that's doing all the work acoustically to control the buildup of activity sound and to help presentations be clear and intelligible. We also got really into the sound isolation design, and we actually did several rounds of this listening demonstration, which resulted in moving doors in some locations and adding vestibules and adding seals around the perimeters of the doors. And all of this information would have been so much more difficult and less compelling to try to communicate through any other kind of single number quantitative parameters that we might use on a more traditional and more straightforward project. 3D listening, now I'll just kind of go into the conclusions now and wrap up. 3D listening, I kind of think, and oralization in general, is sort of it kind of at the same time as the ultimate leverage of acoustical data. I mean, it's all based on the impulse response that we're simulating. And at the same time, it kind of transcends the data altogether. Instead of trying to use as many numbers as we can and find quantitative metrics that fit with our qualitative goals and predict those during design, and then spit those numbers back to the team over the course of design. 3D listening is using all of that information, but it's also kind of removing it from the decision-making process. In other words, the people kind of all involved in this, the stakeholders, were able to listen to what the space is going to sound like in these different configurations and make their decision based on that listening process, rather than trying to decipher, one of our reports, with graphs trying to explain how we were predicting reverberation, or, how much sound we expected was going to get into any of those classrooms. It is kind of the ultimate communicator in consulting, and that's really why it's becoming a growing part of our practice, and why I thought it might be of some interest to folks in the webinar with the background in data science. So I think that just about covers it. Consulting, while I don't have a background in data science, consulting is sort of all about this communication of data and finding ways to map between the perceptual domain, the listening experience, with quantifiable, measurable parameters. So with that, I'll say thank you, and I look forward to hearing your questions.
Thanks, Kelsey. That was fascinating. And I don't think, we've never spoken to anyone quite with your background. So it's a very interesting space to be in. And So much of it, I think, reminds me a little bit of some of the sort of fundamental questions people are asking through natural language processing as well, right? It's sort of this understanding semantics and how do you translate that into quantitative data and trying to figure out what, sort of what's the core meaning of, when you say, I need to be able to hear someone intelligibly.
Right.
It's a very interesting, and it's so personal, and yet you can find that you can establish parameters around sort of universally what is intelligible space.
Right.
So thank you so much. We've got a couple of interesting sort of more general interest questions that I'll start with, and then we'll get into some of the harder stuff.
Sounds good.
We've got someone who asked, are there any third-party certifications you would recommend for someone looking to enter this field? But also just how do you think about, coming into this space, especially in sort of both the engineering aspect of it, but then also the sort of the technical data side of it. Do you have any thoughts on what kind of talent you'd like to see?
Yeah, that's a great question. And I mean, I think the best answer that I can give is that like the more diverse, the more diversity we have in backgrounds of people coming to acoustics, the better off that we are. The sort of traditional paths into acoustics are often through engineering or through architecture. And there's one, like two, very few undergraduate programs that have any acoustics classes, let alone like an acoustics degree at an undergraduate level. So there's a huge variety in where people kind of start, including architecture, many forms of engineering, but also totally outside of that. I mean, there are lots of people who don't have an engineering background that also find their way into acoustics. A passion for music is certainly a common trait among many of us, but it is not a requirement. And there aren't enough concert halls for every single person to work on all the time. So that's kind of, it's a nice thing that ties a lot of us together, but it's not the same for everyone. And when I entered the industry, it definitely was the case at that point that a graduate degree in acoustics was really pretty necessary, because there just wasn't any way to get coursework at the undergraduate level, and the thinking behind the career path was a bit more traditional. And I'm really happy that has started to change over time. And we are trying to look in different places now for candidates to become acoustical consultants, because there's just, that training can really happen on the job. And it's really beneficial to us to see people from all different backgrounds. There is no certification. You don't become like, in engineering, you might become a professional engineer and take exams to have like a specific sort of certification for that. And that does not exist yet in acoustics. So it's a little more freewheeling.
So speaking of music halls, someone also asked, do you have a favorite music performance space in Boston? And also, I'm going to add, do you have a least favorite music performance space in Boston? You don't have to name names on the latter one.
Yeah, that's a great question. I mean, my Boston Symphony Hall is one of the best concert halls in the world, and we're very fortunate for it to be in our neighborhood. And that's a space that, I love going to hear performances at. I was also really lucky to get to play there once. So I think I get to count that on one of my favorite spaces, although it's certainly not a regular opportunity. That was a really unique opportunity. Jordan Hall is also a wonderful, smaller kind of chamber performance venue. And there are all sorts of space, and I think back to the spaces where I grew up playing music, and, to be really honest, I wasn't thinking about acoustics when I was playing piano, and as like in elementary through high school, this is not something that was really on my mind until I was trying to find some career path that would combine engineering and music. I mean, I may have been thinking about it in not as much in an intentional, unconscious way, but when I think now back to those spaces that I played in growing up, I mean, they were not wonderful acoustically. And the kind of classic example is like the high school band room that we're packing a huge number of students into, and it's way too loud, and you can't really hear anyone playing across the room. And that's unfortunately a really common experience, and it's something that we work to try to avoid and create rehearsal spaces where people can hear each other and play well together.
I think that's so true. You take these spaces for granted until you enter a really well-designed one, right?
Right. I almost don't want to return to the spaces that I grew up playing in, because now I can't help but become extremely critical of the acoustical design of the space, and sometimes it's nice to not think so deeply about that and just enjoy the music, because that's what you're really there for.
So we have a question that's a little bit more on measurement. How big is the difference between the spreadsheet models and the real world measurements typically? Do people use more advanced 3D scanning, such as LiDAR, to make more accurate models?
The difference between that kind of spreadsheet model and the real space, it totally depends on the space that we're talking about. So in the example that I was giving of a classroom, like a simple, six-sided box with material information that we know, that there's not a lot, we should be able to basically exactly match our spreadsheet model to what's happening, to what we would measure in the space. But, we didn't even use a spreadsheet model on the Harvard Science and Engineering Complex Atrium because there would have been no kind of realistic way to get those things to match up. And in lots of in music performance spaces and other kind of complex spaces, we do tend to lean more on simulation tools that give us a more nuanced understanding of acoustics. And the most challenging situation, a situation that we're in all the time is trying to understand the acoustical conditions of an existing space where we may be able to know what the geometry is. We may be able to use a 3D scan to understand exactly what the dimensions and the shape of the space are. But the big unknown is what is the material doing acoustically? And we have lots of measured and published data from manufacturers. And so that whole process is us trying to figure out, okay, this thing that we found in the field, what is it most similar to that we can find in this table of absorption data? And a lot of times, especially in older buildings, that kind of comparison process takes quite a long time. And it's a problem that doesn't have one solution because there are too many variables involved there, like too many materials that you don't know enough about. And so, that's a case with a lot more uncertainty between measurement and model.
It's interesting. We also had a question about, is it easier or harder to consult on improvements to existing venues or create something in design? And I think you answered some of that, right? The complexity of trying to figure out what the retrofit looks like or what old materials will do.
Yeah, there's some of both of that, right? Like if you're working from an existing space, at least you can make a measurement and have some and kind of use that to calibrate a model so that what you're starting from is similar to what is there already. Whereas if you're working with a totally new space, you know more about the materials because you're specifying them and you know what's going into the project and what's going to be purchased, and you don't know that in an existing building, but you also don't have a reference point. So you're working from scratch and trusting that the ray tracing algorithm is doing its job.
So about ray tracing, Daniel Goldenholz asks, you mentioned that 3D listening is based on ray tracing and impulse response.
Yep.
What are the types of situations where these assumptions break down?
One of the classic examples is at low frequencies, especially in small rooms. So if you think about a recording studio design, like the smaller the room and the more important it is to understand the acoustical behavior at low frequencies, low kind of bass pitches, the ray tracing becomes totally not helpful to us anymore. The bigger that the space gets, the lower that kind of threshold between low frequencies that aren't predicted accurately and high frequencies that are predicted pretty accurately, that threshold keeps going down as the space gets bigger and bigger. At low frequencies, and again, especially in small rooms, you need to actually simulate the wave behavior instead of treating sound like a straight line as rays that are radiating from a source. You really need to understand the wave behavior, the modal behavior of the room. And that's a lot more difficult to do because you have to find a way to estimate the wave equation, a partial differential equation. And it's doable. There is unfortunately no commercially available acoustic software that does that in a feasible way for kind of on the scale of a room acoustics problem. But this is in development. It's what I focused on in my master's research, and I hope that in the next 5 or 10 years it will kind of come through and help us to make some advances there.
Really interesting. What do you think so someone asked, what are the frontiers you see for injecting machine learning techniques into understanding acoustics? But I'd recharacterize that a little bit to ask, what frontiers you see for just data gathering and data analysis in acoustics? What would be your wish list at this point when you're designing these spaces?
Yeah, it's a long wish list. One of the things that I have spent a bit of time researching recently is the impact of source directivity. So, if you think about popping a balloon or clapping your hands in a space, that sound is going to radiate pretty evenly in all directions. And that's a pretty easy kind of system to understand. When you put a violin in that space, the radiation pattern of that instrument is totally different. It's not radiating evenly in all directions. And that directivity of that source has a really profound impact on what we hear as an audience member. And we have to make assumptions about that. We have to build that into our model. And there's a disconnect between how much information we have, like measurement data on that's kind of usable for us in acoustics, in order to model that really well. And one of the projects that we did a couple of years ago, we made some advances on that in-house. So what we did is we wanted to be able to model a string quartet much more accurately. So we had the string quartet come to our office and all play together, and we had a video recording of each one of them. And then we put each individual musician into an anechoic chamber and put headphones on so they could listen to that recording with their quartet members and watch the video recording so they could play along with it, but we could record them in that anechoic space, which is the kind of recording that we need for simulation. And we could record that with multiple microphones in an array assembled all around that instrument to be able to capture how sound is radiating in all of those different directions, rather than having to make some assumption built into the model. So source directivity is really big. And then the other one that I mentioned in the presentation is just having better. We have so much information in the impulse response, and we have a lot of parameters that we have defined that we'd like to be able to correlate with perceptual attributes. So with things like envelopment or your spatial impression of the space, or loudness. Over the years, there are a whole slew of quantitative parameters that have been developed to try to map to those things. And unfortunately, most of them are just not very good. Or they're good in some cases, but not in others, or they're not reliable to measure. And, it is kind of a question to me as to whether we sort of move beyond those single number parameters altogether, if we really don't need to use that anymore, because there's no way to distill the concert hall acoustics, down to some kind of summary like that. But it sure would be nice to have some more things beyond reverberation time and, more reliable than some of the other metrics that exist.
Interesting. I think we have time for one more question. So I'm going to give you a fun one, which is any tips on how to improve the ambiance of a home music or movie room?
Oh, okay, that's a good question. I just did that for my playroom downstairs. I mean, most of this comes down to, it could apply to any of those three areas, right? Room acoustics or sound isolation or noise and vibration control. The noise stuff and the sound isolation stuff is going to be really hard for you to do something about without ripping out the walls and the ceiling and building it again. But the room acoustics is something that has to do with all those interior finishes. So, in most homes, people have sound reflective, hard, drywall wall surfaces all around them. And in a movie watching space or a listening room or something like that, you'd really like to get some more absorption, especially if your loudspeakers are facing directly at a sound reflective hard flat wall. You'd like to put some absorption there, like something that is thick and soft, like a big fabric wrapped fiberglass panel or a curtain, or something along those lines that's going to absorb sound rather than send back a hard reflection into the room.
Well, thank you. Thank you for your time and
Sure.
clearly, all your expertise in sharing that with us. And thank you to our participants for their really great questions. This is it for us for this term. And so we'll be online soon with our next list of industry seminars. But in the meantime, we wish you all the best for the holidays. And thank you very much. Thank you, Kelsey.
Thank you.